Thank you very much. Good morning from my side as well. Thanks for the introduction. Indeed, I'm in the lucky position that these are two fascinating projects, and I have the pleasure to be working in both of them. This is why I had to wear a neutral shirt today. And I'm going to briefly go over the energy efficiency part in both projects. As said, I've been involved from the beginning, so that means that actually more than 3 years ago we all sat down in both of the projects, and we basically were looking at a blank sheet of paper, and we thought, okay, man, let's do something about exascale. What do we do, right? And then of course I had to think about scalability, and with scalability comes ideas like programmability. But one of the things that always popped up in these discussions is we cannot afford exascale energy efficiency. We cannot afford exascale without having a significant leap ahead in energy efficiency. So this is really important. I mean, really, really important. So what do we do for energy efficiency? Well, I think one of the reasonable approaches is look at low power CPUs. Look at the ARM space, look at what's coming from the embedded mobile market. That's fairly reasonable to do, and I think Filippo was nice enough to thoroughly cover this in his presentation. We're also sure that accelerators is probably a way to go, and usable means of accelerators. And I think Norbert could make that point fairly clear. And so I consider that covered as well. But this all contributes actually to higher throughput and also higher efficiency, higher energy efficiency. So next thing that we looked into is efficient cooling. And well, this has not been covered. And we'll also take a look into sensors, and even more sensors at high frequencies. Filippo hinted a bit at why this is important, and I'll go into that as well. But let's start with the cooling. What do you do? Why would you want energy efficient cooling? Well, first of all, energy efficient cooling means you are just improving the ability to remove that waste heat that you're producing with these machines from your hot components. And if you do so, you can basically pack things tighter, you can improve the density, you can improve the performance. Is also good for exascale. Another thing is, if you improve the heat removal, then you can actually run at higher inlet temperatures. What does that mean? Well, if you can cool with higher inlet temperatures, you can use year-round chillerless cooling. All of these data centers nowadays have large chillers, and there are energy-hungry chillers that need to produce cold to get rid of the heat of your computer. If you can get rid of those chillers, you're already saving on energy and operational costs. And another advantage of having higher temperatures is that you can, of course, make better use of that waste heat, for example, for heating in winter, or we have some experiments where we're actually investigating heat reuse for cooling. So how would you do that? Well, ideally, you can do that single phase by using water. It's the best from the physical properties that you could get for cooling. You can also follow a two-phase liquid cooling approach. For example, you've seen all these bubble baths in the exhibition hall with this 3M Novec fluid. There's some things to pay attention to that, but it's one of the solutions, certainly. And we're looking into these technologies. So in the DEEP project, we are, for 3 of the big machines that we've rolled out, the cluster and the booster and the small energy efficiency evaluator prototypes, we are using a aluminum cold plate approach that is capable of cooling all your components on the board with water very efficiently. And for our little ASIC evaluator, in which we test the performance of the Axel ASIC chip, we need a little quicker solution because that came in quite late in the project. So it's quite reasonable here to go with this 3M Novec base, in which it's let's say a bit more flexible, but certainly probably in this setup, in this very current setup, probably not suited for a 10 years operation lifetime. So that's as much as I would like to go into detail about cooling these days. I think you've seen all the liquid cooling offerings from the vendors anyway. I think everyone has understood that by now. So let's talk about sensors. And to talk about sensors, I would actually like to show you how we do power monitoring in Mont-Blanc. So Filippo has shown us that we have like a blade architecture. We actually have 15. We have 15 of these Samsung Exynos boards within a Mont-Blanc blade, and these are interconnected through a midplane. So let's remove them for a second for the illustration. And on this midplane, we have for every of these node cards a power monitoring chip. It's a fully integrated chip that measures the power and supplies the power measurement data over digital I2C bus. We're collecting this information. This is a very high frequency, so this is I think sampling at 70 kilohertz or something. And we use that high frequency data and aggregate that in an FPGA that's on the board to do some averaging. And then we basically forward 1 second average values for each of these nodes into a board management controller. And the board management controller, we'll get back to that, is our source of this power monitoring data. Now switching over to deep. This is the very, very, brief overview of the deep booster node card design. You can basically see the two Xeon Phi cards here. They have some sensors on their own. You can see to the left our networking board with the two XTOL, with two FPGAs which implement the XTOL interconnect. And again, in the left lower corner, you can see we have a board management controller, and essentially the message of this scheme is that this board management controller again is capable of collecting all these sensors that we put of the sensors that we put on these custom redesigned boards. So all in all, both prototypes, or each of these prototypes, has way over 1,000 sensors, and that's that's already something in terms of monitoring. However, we also decided that we would like to have additional information from sensors that are outside the system, sensors that originate from the infrastructure for cooling around these systems, integrate into the global monitoring system, and we would like to have all of these sensors report at very high frequencies. So typically, standard system monitoring tools, they give you maybe a reading of once per minute, because they use a standard pull model, so you have like a management server that queries one sensor after another, and we thought we need something at higher frequencies and ideally have some push model for that. So this is how we aggregate all these information. So you've seen in both projects we have our board management controllers doing the very low level sensor acquisition. However, we also created some kind of software connectors for integrating monitoring data that we get from elsewhere. For example, IPMI protocols, a standard management protocol for servers. You get lots of in-band information from your sysfs, for example, the CPU frequency that you're running at right now. Or maybe your CPU die temperature. SNMP is another standard management protocol that we're supporting, and also we have a software component to aggregate further, let's say, information that you get from log files, for example, and you can basically extend that list as you wish. And we're using a very, very lightweight messaging protocol called MQTT. It's something originating from the Internet of Things space, buzzwordish, but it's quite useful for our purpose. And we basically feed all the information from those various sources at high frequency into a component that we call the collect agent, from where it is being stored into a database. Now, scalability is, of course, a concern, and as you see, I mean, as it looks right now, this collect agent and the database would probably be a scalability bottleneck if you go to larger sensors and higher readout rates. That's why the whole system is actually designed in a fashion that you can duplicate or add as you wish database nodes and collect agent instances, which enable you to basically linearly scale this entire setup, meaning that if you're running low on the performance of this database, then you just add more of the database service for your monitoring. The nice thing is, since we're using a distributed key value store, this still is visible to the user as if it was one single big database, although it is stored in a distributed fashion. And that also means we can basically implement a system where we store the monitoring data locally, meaning close to the sensors where it's being acquired, nonetheless run global analysis on this data. And to wrap up so that we can actually also enjoy the last 15 minutes before the break to ask some questions, I would actually go back to one of the examples from the Mont-Blanc project, because indeed we rolled out that toolkit for Mont-Blanc first, and we gave it into the hands of the application developers. And again, this is a curve that was done by some people working on the Himeno benchmark, analyzing a node. And when they started off with their very first unoptimized initial version, the power trace looked like you can see in this red curve. So the application runtime was almost 130 seconds, and then after tuning that application, porting it to OpenCL and OpenPSS, you would end up with a power trace that is in this blue curve, so meaning that you might consume more power for the runtime of the application, but the application finishes much faster. And having this granularity at, let's say, second power sampling intervals that we could give with this solution to the application developers, it meant that they could get this kind of information much faster and have a much shorter, let's say, development and optimization cycle. Because, I mean, with the standard system monitoring of where I get a reading of once per minute, I would just get 2 readings. I could not even capture the effect that we are seeing. You could maybe mitigate by running the application longer and making those test cases longer, but that means you have a much slower development and optimization cycle for these applications. And so we are glad to see that this is actually being used and seems to be useful to people. I think Filippo could also make that clear in his presentation when tracking down these cooling issues. And we know that the solution that we've developed for those projects does scale and enables us to do that. So going back to my titles, I would say when it comes to exascale, more sensors will not be more problems. So thank you very much.